Hi, everyone. Thank you very much for being here, and thank you to all the organizers for giving me this nice opportunity to talk about my recent work. I'm Yusuke Mikura, a postdoc at Academia Sinica Institute of Astronomy and Astrophysics in Taiwan. Today, I'd like to share with you my recent work with Teppei Okumura and Misao Sasaki on the imprints of gravitational wave polarizations on the large-scale structure. Let me start with my motivation. It is widely believed that prior to the Big Bang cosmology, there was a period of accelerated expansion called inflation. In the simplest model, inflation is described by a scalar field combined with general relativity. And a key prediction of this simplest model um, is the presence of curvature perturbation and the primordial gravitational waves. While this model or this scenario is known to be successful, we don't know much about the details. For instance, we don't know the origin of a scalar field, and we don't know whether or not other Moores in the metric perturbations were present during inflation, and we don't know whether or not the primordial gravitational waves are chiral or not. Understanding these details is crucial for both cosmology and particle physics. In order to investigate the tensor perturbation, it is very important to use not only CMB, but also the large-scale structure, considering the wealth of upcoming cosmological surveys. A natural question is how we can probe the tensor field using the large-scale structure. One possible method is to use the intrinsic alignments that are the correlations between galaxy shapes and the surrounding large-scale structure. A galaxy shape is primarily affected by the gravitational potential through the tidal forces. Here, gamma ij is the galaxy shape field, and the delta represents the matter density contrast. While the gravitational potential is a dominant contributor to the intrinsic alignments, the galaxy shape can also be uh, influenced by the tensor perturbation because the galaxy shape is proportional to the Riemann tensor, that is the function of the tensor perturbation h. For subhorizon Moores, this red line is given by hij, then the gamma ij, the galaxy shape field gamma j, is roughly proportional to the hij itself. So by studying the intrinsic alignments, in principle, it is possible to extract information about the tensor perturbation. So intrinsic alignments can serve as an interesting tool to probe the primordial universe. However, it is challenging to extract the pure helicity-two Morse from the galaxy shape correlation, because the dominant contribution comes from the gravitational potential. Therefore, we need to identify suitable correlations in real space or on the sky um, to extract other Morse in the metric perturbation. Okumura and Sasaki showed that in the minimal setup, including the helicity-two Morse and the gravitational potential, pure signals of the helicity-two Morse can be obtained by studying the correlations of the derivative of the tensor perturbations on the two-dimensional sky. And they show the explicit form of the kernel gamma connecting the correlation function and a power spectrum. This work is limited in the sense that they include the helicity-two Morse and the gravitational potential. In a generic theory of gravity can accommodate up to 6 polarization, so it is natural to ask how other Morse beyond general relativity affect the kernel gamma. So in the following, I will study the effect on the counter gamma. To study, let me start with defining the tensor perturbation. In three-dimensional space, the tensor perturbation can accommodate up to 6 polarizations, which are labeled by the helicity lambda. There are helicity plus minus 2 and the plus minus 1, and the helicity 0, 2 helicity 0 mode. The one is breathing, and the other is called the longitudinal. And I use the synchronous gauge in this work. This longitudinal mode corresponds to the gravitational potential, so we assume that this longitudinal mode is dominant contribution. With this tensor perturbation, we can define the Perl spectrum, and we write the Perl spectrum pH here. And under the assumption that a gravitational wave background is an isotropic and is stochastic, the cross-power spectra between the different helicity modes vanish. So for each helicity lambda, we can define a power spectrum, and we write it as a p lambda. Now we are interested in the subhorizon dynamics of the tensor perturbation, and we write the wave equation as follows. And we put c lambda here to allow the wave propagate slower than the speed of light. The solution of this wave equation is given by this. And for each lambda, there is a cosine function in front of the p lambda initial. And this p lambda initial is an initial Perl spectrum that are fixed by inflation. Now we defined the 3D Perl spectra, and we are then moving to the projections onto the two-dimensional plane. We need a projection because the galaxy shapes are measured as two-dimensional images. To introduce the projection, we first introduce the coordinate in a real space. And I write the coordinate in x, y, z, and choose z as the direction of the line of sight. And for the orthonormal basis, we write E1, E2, and K. And we choose the E1 so that it aligns with the coordinate x. And we write the directional cosine between the angle between the line of sight and the wave vector k as theta k. With this setup, we can write the orthonormal basis in terms of the coordinate in this way. And we define the projected space with the first two components, which means that the projected space is spanned by x and y. Then using these the first two components, we can define the projected polarization tensors, which I write E lambda AB, and we use the indices capital A, capital B for the projected space. And with this, we can define the projected tensor perturbation, HAB. Now we further remove the trace bird of the projected tensor field because we are not interested in the magnification. And the trace can be easily removed by this operation. And a trace-free two-dimensional symmetric tensor has two components, which is HTXX and HTXY. And they are given by this. And we see that it is easy to see that the autocorrelation of HTAB is parity even because this correlation is a sum of the square of each component. And there is no helicity mixing. So 0, H plus 2, H minus 2. And the autocorrelation is simply can be written as this. and the function f is given by this. Now pt is the sum of p plus 2 and p minus 2, and b is plus 1 plus p minus 1. And this mu k is a directional cosine. What we can see from this is that this autocorrelation includes the longitudinal contribution that is much bigger than the helicity-two or helicity-one contribution. So by looking at this autocorrelation, it's difficult to obtain the information about the helicity-two or helicity-one mode. So we need to introduce a different operator. So we define the lower rank vectors using derivatives in the two-dimensional space. We can define two vectors. One is VTA, and the other is V tilde. And with this expression, it's easy to see that autocorrelations are pretty even because the autocorrelation is the sum of the square of each component. And again, these autocorrelations contain the longitudinal mode, so it would be difficult to obtain the to see the helicity-two contribution. However, the cross correlation V tilde V is free of the longitudinal contribution, but is a parity odd, which can be seen as this equation. Here, the chi t is a parameter for the of the chirality defined by the p plus 2 minus p minus 2. And chi v is the same. So if in the helicity-two or helicity-one sectors, if there are parity violations in these two sectors, this cross correlation is a suitable object to study the parity violation. However, if there are no parity violation in the helicity-two and the helicity-one mode, the cross correlation becomes 0. So we need to introduce the additional field. So we define the scalar field using derivatives. And we define the S tilde by the two derivatives and the one totally antisymmetric tensor. And after some calculation, we can see that this autocorrelation is parity even and free of the longitudinal contribution. So this autocorrelation is written as the helicity-two contribution plus helicity-one contribution. And we see that the mu dependence in front of the power spectrum for the helicity-two mode is different from the coefficient of the helicity-one mode. And in the real space, we integrate this mu k. So in the real space, by matching by the template matching, it would be possible to distinguish these two contributions. Let us now define the kernel function relating the correlation function and the power spectrum. And we call the kernel function the overlap reduction function, borrowing the terminology used in parser timing array. And here I defined the two ORFs. One is for the scalar autocorrelation, and the other is for the vector cross correlation. And in order to write the ORF in this way, we have to set the two the coordinates, and I put the one galaxy at a point x prime at a distance r prime, and I put another galaxy at point x at a distance r. And geometrically, the ORF is a function of the r and the delta r, which is defined by the r prime minus r, and also the theta is the angle between two galaxies. And also, we assume that all helicity has the same characteristic, meaning that the power spectrum of helicity lambda, the initial power of the helicity lambda can be written as the fraction in lambda times the pH initial. And here we also assume that the helicity-two Morse propagate with the speed of light. And this ORF, of course, depends on the propagating speed and also the fraction of n lambda. Let's see some examples. The first example is the scalar autocorrelation. First of all, let me fix the propagating speed of the helicity-one mode is equal to the speed of light. And the overall reduction function has this kind of function, and the overall oscillation is controlled by the same cosine function. And the amplitude is determined some coefficients and the fraction nt and nv. The upper panel shows that the upper panel are depicted by fixing the kr equal 1, and the lower panels are for lower panels the kr is fixed to 5. And from left to right, the delta r increase, so the same redshift to the different redshifts. And the black dashed line is the fiducial line, and t equal 1 and v equals 0, so no helicity-one mode. It is apparent from these figures that the overall amplitude is very different depending on the fraction nt and nv. So it would be possible to distinguish the nt and nv by just looking at the scalar autocorrelation, even if the CV equal 1. If CV equal the CV is different from 1, there is a deviation if we look at the finite delta r. So if we look at the different finite delta r and performing the template matching, we can it will be possible to distinguish the helicity-two mode and the helicity-one mode using their real data. Then the next example is the vector vector cross correlation, which is suitable for the parity violation. Now, first of all, let me fix the CV equal 1 here. In this case, the overall function is almost the same, and it is not clear whether or not we can distinguish these two by the template matching. But if the propagating speed is different, we can it would be possible to see the difference because the sign of the overlap reduction function can be different with a finite delta r. Let me conclude. Intrinsic alignments can be an interesting tool to probe the primordial universe. And the scalar and the vector fields constructed from the tensor perturbation on the sky allow us to extract the helicity-two and helicity-one Morse in the presence of the large longitudinal contribution. If the propagating speeds of the helicity-two and the helicity-one Morse are different, it would be easier to distinguish them through the template matching. In this work, I relied on a flat sky approximation. So it should be extended to derive the full sky expressions. And of course, it is important to study its detectability, which is my future work. Thank you very much.